Now, to understand the fabrics of dynamic design, let us again take a case and walk through the approach. Let's consider a case where we have to design a robust barcode scanning technology, applying which the barcodes will remain accurate and precise in all weather and lighting conditions. So here the output response is the measured width of bars and spaces between the bars of the barcode. This measured width will depend on the actual width of these bars and spaces. So in this case, the actual width becomes the signal or M, and the measured width becomes the output response Y. Let's assume that the signal has three levels, that is, the sample barcode has two black vertical bars of different width and a white space in between. We know that as a producer, one cannot control the ambient lighting condition in which a user will end up using the scanner. Having said that, we also know that ambient lighting will play a critical role in effective scanning. So it becomes a noise factor which user may not bother to control, but our product should be robust enough to handle such constraints. So we will consider two levels for this noise factor. The input control factors would include the barcode distance from the scanner. We will take this as factor A, the mirror radius, which would be factor B, and the aperture, that would be factor C. Each factor has two levels. The factors and their levels are summarized here in the table. The control factors, they have two levels. The signal has three levels, and ambient lighting, which is the noise factor, is considered at two levels. First step is similar to what we saw in the static design approach, where we determine the degrees of freedom. Since we have factors at two levels, we lose 1 degree of freedom for each factor. So the total degrees of freedom will be 3. Total number of experimental runs will be 3 plus 1, that is 4. And since the suitable orthogonal array should be greater than number of experiments, which is 4 in this case, we select the nearest orthogonal array that follows a 2 to the power n series and is greater than 4. So in this case it will be L8. Next, we need to form the required linear graph. Since in this case we have to study only the main effects for the factors A, B, C with no interaction effects, the required linear graph will be quite simple, each factor being represented by a node. For L8, this is the standard linear graph. And then we modify this standard linear graph to match our required linear graph. Now we allocate factors to the columns in the selected array. So the first factor A is assigned to column 1, B goes to column 2, and C goes to column 4. This is the standard array layout for L8. Since we allotted factor A to 1, B to 2 and C to 4, we will choose the first, second and fourth columns from the default array. So this gives us the final experimentation layout for this example.